Hello everyone, I'm Yuwei Zhang. I'm a postdoc working with GWF and PNL. I'm going to talk about anthropogenic aerosol impacts on deep convective clouds and precipitation over Houston. As we all know, aerosol cloud interaction has large uncertainty in predicting their impacts on weather and climate. Cloud microphysics parameterization is one of the important factors leading to the large uncertainty. So our first objective is to understand how anthropogenic aerosol effect is influenced by cloud microphysics schemes. For the Houston region with urbanization impact, the anthropogenic aerosol effect may also work together with the urban land effect. So our second objective is to investigate the joint effect and the respective effect of both anthropogenic aerosols and the urban land. We use WRF-Chem at 500-meter resolution to simulate a case on June 19 in 2013. As we can see here, our simulation using spectral beam scheme with anthropogenic aerosol can get the similar strong convective cell over Houston as that is shown from next radar. For objective 1, we did the simulations by using Morrison two-moment bulk scheme and the spectral beam scheme with or without anthropogenic aerosols. To explain the differences in aerosol effect, we also use modified Morrison, which is based on Morrison scheme but replace saturation adjustment approach with condensation evaporation calculation based on explicit subsaturation. For objective 2, we based on the simulation with spectral beam scheme, we further did two sensitivity tests by replacing the urban land with the surrounding cropland. By comparing the composite reflectivity at peak time with next radar, we can see that the simulation using spectral beam schemes gets the storm much better in both location and high reflective value. For the Morrison scheme, it gets several small convective cells. From the results of CFAD of reflectivity, we also find that simulation with spectral beam scheme is in a better agreement with observation compared with that using Morrison scheme in terms of the vertical structure of the high reflectivity range and also echo top heights. With the spectral beam scheme, we see a significant invigoration effect on convective intensity and precipitation by anthropogenic aerosols. However, this aerosol effect is much weaker in Morrison scheme. With the spectral beam scheme, the invigorated convection corresponds to the increase in thermal buoyancy, which is induced by the enhancement in latent heating from condensation and ice-related processes. While in Morrison, the increase in latent heating profiles is much less, leading to the fact that the anthropogenic aerosol effect is not significant. This is because that the saturation adjustment in Morrison removes the dependence of condensation on droplet properties and also limits the ice processes by a more efficient conversion of droplets into raindrops. That leads to less cloud droplets being transported to the altitudes above the freezing level. When we replace the saturation adjustment approach with the condensation evaporation calculation based on the explicit subsaturation, which is shown in orange line, we see a similar aerosol effect as that from the spectral beam scheme. We also find that anthropogenic aerosol effect can work together with the urban land effect. Their joint effect can significantly enhance the convective intensity and the precipitation. Overall, the anthropogenic aerosol effect is much more important than the urban land effect. For the convection at low level, for example below 6 km, both aerosol effect and urban land effect are important. For the convection at high levels, the aerosol effect is much more significant. Although the urban land effect does not impact the precipitation intensity much, it initiates the surface rain by about 30 minutes earlier. The urban land effect is important for the convection at low level because urban land effect can strengthen the sea breeze circulation and thus leading to a faster transition from the warm cloud to mixed phase cloud at about 30 minutes earlier. This also explains the earlier surface rain. The aerosol effect speeds up the development of the mixed phase cloud into the deep convection by about 40 minutes. After the clouds develop to mixed phase stage, aerosol effect becomes evident only through the enhanced condensation heating at 6 to 9 km, which accelerates the development of storm from the mixed phase cloud to deep clouds. At the deep cloud stage, the anthropogenic aerosol is more significant than the urban land effect. For the conclusion, here we investigate the impact of anthropogenic aerosol on the convective intensity and the precipitation of convective storms occurred on June 19 in 2013 over Houston, with the WRF-Chem using the Morrison two-moment bulk scheme and the spectral beam scheme. We find that the spectral beam scheme predicts a deep convective clouds agreeing better with observation in terms of reflectivity and the precipitation compared with the Morrison bulk scheme. With the spectral beam scheme, we see a significant invigoration effect on convective intensity and the precipitation by anthropogenic aerosols. Whereas the anthropogenic aerosol effect is not significant with Morrison scheme, mainly because of the saturation adjustment approach. We also find that the anthropogenic aerosol effect can work together with the urban land effect to significantly enhance the convective intensity and the precipitation. By comparing with the urban land effect, the anthropogenic effect is much more important. The urban land effect enhances the sea breeze circulation, leading to a faster transition from the warm cloud to mixed phase cloud. The anthropogenic aerosol effect becomes dominant after the clouds evolves into the mixed phase clouds, accelerating the development into deep clouds. Thank you.